We're talking, last time we were doing method of joints for trusses. We're going to continue. We're actually still on method of joints, but zero force members. And we're going to use this same truss here to look at our zero force members. And actually, let's start. We'll use that same truss here, but for zero force members, let's write down how we are going to find these, and also why do we have zero force members? Well, you know, in our particular truss over here, we have a weight here and we have a weight here. Well, we could have a different loading scenario, in which case they would be loads in different members of that truss. So they could be used for, for different loads. Maybe we move the loads around. And so when we move those loads around, we end up with zero force members in different areas. And then another load case, we have zero force members in other areas. The other reason, and we'll see that when we start working on our problem today, is just kind of overall stability. And so that overall stability, we're just talking about kind of having everything tied together and kind of integrated together there. And so we're going to identify our zero force members. We can find all zero force members with something called search and destroy. And so what we're going to do with this search and destroy is we're going to draw FBDs at joints that meet the following conditions. And those conditions are only two meet. So only two members meet. That's one of them. And then our only other condition we need to look for is three members meet and two are collinear. What collinear means would be like I have like one right here and I've got another one right here, and then maybe I have a third one that's coming in right here. These two, this one and this one right here, those are collinear. So this one and this one, those two are collinear. It just means they're in the same line to be collinear. So then we draw the FBD and we'll use equilibrium in the X and the Y and see if any of those are specifically equal to zero. So we were like specifically looking for something to say, yes, it is exactly equal to zero. Okay, so let's go ahead and let's redraw our picture. We're continuing the same problem as last time, but let's redraw our picture because we're gonna label it and we're gonna want to like destroy stuff on there. And so let's not use the same one that we had last time. So our overall outline here is this parallelogram, right? It basically looks something like that. And then we have a vertical here, and we have a vertical here, and then right here, and we have some diagonals right there. So there's basically our outline of our overall truss, same yardstick truss that we've been working on. There's a 1.96 newtons right here, and then we have our 4.905 newtons right here. And then we found out last time that we had this AX and this AY, and we had found our AY right here to be equal to a 3.93 newtons, and then we have our AX right here, and then we had CY, and we had found CY to be equal to 2.94 newtons. And so we've already solved for the FBD of the whole truss. We found all of our unknowns there and for those support reactions. And then let's also label our points. So this was point A, point B, C, D, and then we had E, F, G, and H right there. And so what we're going to do today is we're going to, part B was to ID all the zero force members. Okay, so we have, let me scroll back just a little bit so we can see our search and destroy. We have two criteria. We only have two things that we need to look for. We have only two members meet. Well, where do only two members meet? Well, they at D, right? And actually we already looked, last time we had already looked at D. So for our solution, let's look under only two meet. And so right now, the only places we have only two that meet are D and E. And last time, we looked at, we already looked at D. And we did not find any zero force members. So no zero force. So we looked at D because what we're specifically looking for is the equilibrium equations to tell us, yes, that explicitly has to be equal to 0. Well, D or E now meets our search criteria under our search and destroy. So let's do an FBD at point E. If I do an FBD at point E, what we're going to draw, remember everything in tension. So A to E is going to go up and to the right because it's going away from point E. That's a tensile force. And then I'm going to go to the right on E to F because that's going, again, away from point E. And so everything is drawn in tension. I didn't label any of our geometry on our picture there, but if we remember from last time, that's a 45-degree angle right there. And then also want to tie this back to our learning objectives. Our learning objectives was that we needed to be able to identify all the zero force members in a truss. And so that's what we're focusing on to start with here today. Okay, so we've got this FBD right here. There's no forces applied to that in our particular loading scenario. And so let's take a look. If we sum forces in the X equal to 0, well, actually, maybe I don't want to start with X because that's going to have two unknowns. Why don't we start by summing forces in the Y? Because I'm only going to have one unknown. Well, sum of forces in the Y, I'm going to have AE times the sine of 45, and that's everything in the Y direction. That has to be equal to 0. And so what's the only way for the sum of forces in the Y to be equal to 0 to happen is for AE to be equal to 0. So we got an explicit equation that said AE is going to be equal to 0. We can go on to our next equation. Sum of forces in the X direction is going to be equal to 0. Well, if we write everything in there, and if I have my positive sign convention going off to the right, I did my positive sign convention and Y going up, going back to that sum of force in the Y equation. Now moving ahead to sum of forces in the X equation here, So we're going to have AE times the cosine of 45 plus EF has to be equal to 0. Well, we know AE is 0. So again, we got explicitly EF is equal to 0. So we can destroy these now. So let's come in here and let's see what color. Let's use green. Let's destroy these. So EF goes away and EA goes away. So we've literally destroyed those. And so there we go. We've got a picture of the truss there. Remember these, I took these off. There used to be one there and there used to be one there. We destroyed them. And look, it's still holding up the load right there. Everything is fine. Those did not have any force in them. Now, the reason we have to destroy stuff is because that can open up another joint for us. F now only has 2 members. So what are we going to do? We're going to do an FBD at F. And if we look at F now, we have a force, an unknown force, F to G. We have an unknown force, F to A. And I'm drawing everything in tension. We also have this 4.905 newtons. Are we going to have any zero force members at that joint F? Do you think when we start summing forces, and do we even need to, like, we can get to the point where we don't even have to write out our equilibrium equations. You maybe even could get to the point where you don't even have to draw the FBD. That's a little bit more dangerous, but if you get good enough at this, you can look at it and be like, okay, you can visualize what the FBD would look like and then do your equilibrium equations and figure it out. Let me ask somebody in the front row here. How about Robert Warkentine? Do we have any zero force members at F? Is FG or FA 0? I see, I don't know if Robert...
I believe so.
Yeah, which one, Robert? Well, we could do our equations, right? Sum of force in the x is equal to 0. What do we have going on in sum of force in the x? Just FG, right? So FG would be 0. And then what if we sum forces in the y equal to 0? Well, actually, we're going to find we have an FA, we'll do positive going up. We have an FA minus 4.905. So FA is not going to be equal to 0, but FG is equal to 0. So let's go back and let's destroy FG. So FG goes away. Now I'll come back up to those, but if we look now, oh look, there we go. We got rid of FG. FG is just kind of hanging down there in our yardstick truss, and everything looks totally fine, doesn't it? We're still supporting all those loads, so we didn't need any of those. We didn't need this yardstick. We didn't need that yardstick. We didn't need any of those. And so all those go away. But think about back to the overall stability. Do you think, like, if the wind blows, this is just kind of going to swing in the breeze out here, right? It's going to move back and forth. Do you think, maybe originally that yardstick truss, would you walk across it? Maybe. Maybe if it was like put together a little bit better, right? But now would you walk across there? Probably not, right? Because it's like, okay, that doesn't look like it's really held together very well. So again, right, we need them for different loads, but we also need them for this just kind of overall stability. Okay, any questions? I'm gonna go, let's grab, so we've destroyed all this stuff here. I'm gonna try to grab this and put it, Oh no, what did I do? Undo, undo. Thank you. Okay. I'm going to put it. Oh wow. Yeah, that really grabbed a lot of stuff, didn't it? Okay, let me see if I can get a hold of this a little bit better. There we go. Okay, so we've got our truss there. And so we've destroyed those 3 members so far. But what about now our other search criteria? So I think we've exhausted 2 members meet, right? Well, we've already done D, so we're good there. A, how many does A have? A has 1, 2, 3. But we don't need to look at it. None of them are collinear. G, it's got 1, 2, 3, 4. So too many. We don't need to look at it. H, there's only 3, but they're not collinear. We don't need to look at it. If they don't meet our search criteria, we don't have to look at them ever. But then remember, we do open up some new joints when we destroy them. And so we definitely have to destroy stuff. B does meet. Our 2 meet and 3 are collinear. So let's take a look now at an FBD at B. This falls under the 3 meet and 2 are collinear. So if we do an FBD at B here, we're going to have everything in tension. Remember, pulling away from B. So A to B is going to go to the left. B to C is going to go to the right. And then B to G is going to go down. That's everything that's going to occur at that FBD. There's no applied forces, right? AY is outside of our circle there at B. CY is outside of that circle. Those are the only 3 things we have. Now, if we sum, when we're collinear, if we sum forces in the direction of our 2 collinear forces, the only thing that it's going to tell us is that AB is equal to BC. But that's not telling us that it's equal to 0. We're looking for it to be like specifically equal to 0 like we saw in the previous ones. Now, what about if we sum forces in the Y? If we sum forces in the Y, the only thing we have is minus BG. And so that has to be equal to 0. So we have a minus BG equals 0. So BG is equal to 0. So we better destroy BG then. So we get rid of BG and we can look, okay, does that open up anything? Well, I guess technically B only has 2 meet, but we just looked at B, and when we sum forces in the X, we found that AB is equal to BC, but we didn't really find much else from that. And we could look, make sure that there's nowhere other joint that now meets our 2 search criterias. There is not for this example, and so we're done. We have identified all the 0 force members, and our truss now is going to look like that. So there's all our 0 force members, all our 0 force members are taken out. Again, doesn't look very tied together. We have this this joint right here is like sagging down a little bit there. But we're still holding load, aren't we? We've still got the load there, and we've still got the load there. So we didn't really need those to support the load. For overall stability, yes. Or for a different loading case, yes, we could absolutely need those 0 force members. Any questions? Okay, so search and destroy. And the only, so really, I mean, it's not the only way, but the most efficient way, most effective way is that search and destroy to find all those 0 force members. I'm going to go through this one, but I'm going to go through it quickly. I encourage you all, this is up on the class examples under the supplementary problems. I encourage you all not to try to take notes, but to let's think about the thing that we just did and see how that's applied to a problem that we would see in the homework or on an exam. 2 meet, that is A and E. So I look at A and E and I say, okay, well, let me draw an FBD. At A, I would have an AB as unknown. I would have an AH as unknown. And I'm also going to have an AY and an AX, right? Now, when I sum forces in the X and I sum forces in the Y, even though I don't know what AX and AY are equal to, I'm not going to find a specific equation that says that AB or AH are zero. So AB and AH, those are not zero force members, but I identified that two meet right there, and so I'm going to do my FBD. If I sum force in the Y, AB is going to be, something greater than or let's just say, I don't know if it's going to be negative or positive, but let's just say AB is not going to be zero, and also AH is also not going to be zero. Same thing will hold at E too. Because I have this EY here, at E, my DE is not going to be equal to zero, and FE is not going to be equal to zero. But again, we draw the FBD, we sum forces, and see if it explicitly tells us it's zero. Okay, so there's our two that meet. Now, how about 3 and 2 collinear? So 3 and 2 collinear would be B, G, and D. And so if I look at B right here, well, B, I am going to draw my FBD. I'm going to have a collinear one here, B to C. We will have a collinear one here, A to B. And we will have this B to H right there with a force here of 2 kilonewtons. So when we sum forces, well, one of the things we have to think about is, do we incline our axes? If we have more things on the incline your axes. If we have less things on the incline, then keep them horizontal vertical. Well, in this case, we've got everything on an incline. So I'm going to incline my axes. I'm going to sum forces in the X, sum forces in the Y. BH is not equal to 0 because of that 2 kilonewtons. Now, how about over here at D, which is very similar to B, but at D, we don't have that 2 kilonewtons. So we're going to have these 3 forces, and we are going to find that DF is equal to 0 when we sum forces, again, on an inclined axis. When we sum forces in the Y, we're going to find that DF is equal to 0. Okay, so let's destroy it. Oh, look at that. It just opened up F. So when now we need to look at F. We're going to have an FE going to the right. We're going to have an FG going to the left. And we're going to have an FC going off at an angle. Now, even though I have this angle here, theta, when I sum forces in the Y and I'm back to a horizontal and vertical axis, I'm going to have FC sine theta is equal to 0. The only way for that to happen is for FC to be equal to 0. So now FC goes away. That's a 0 force. Right here at G now, that meets our criteria as well. So I've got a GF, and we have an HG, and then we have a GC going straight up. This one, when I sum forces in the Y, I'm going to find that GC is equal to 0. So GC goes away. So that's how we can use our search and destroy, and you can see I'm starting to kind of abbreviate my process. Don't feel like you need to start abbreviating your process. If you start getting comfortable with it, start abbreviating that process. But that's how we would use that search and destroy for a problem on the homework or the exam. Any questions? Somebody has a question. I know they do. Somebody's got to be thinking about that 5 kilonewtons up there at C. Right? How can GC be 0 force when there's 5 kilonewtons? Right? What about this 5 kilonewtons up here? Like, what is that thing doing? Oh, yeah, okay. Alex is just, yeah, right. Yeah. What about the 5 kilonewtons? Well, it's going to go down this one. It's going to go down this one. It's going to go down this one. The key is that to meet equilibrium at G, is it possible to, right? I drew an FBD right here at G. is it possible, like if I said, well, GC is equal to 5 kilonewtons, what is balancing with that? There's nothing, like if I try to sum forces with GC equal to 5 kilonewtons, I'm saying the sum of the forces is equal to 5 kilonewtons, which means that point G is moving. And so the really cool thing about free body diagrams is that you will never get an FBD at one location that contradicts an FBD at another location. And we have to meet equilibrium for each FBD. It is the only way we can meet equilibrium at point G is if GC is equal to 0. So it is not equal to 5 kilonewtons. GC has to be equal to 0. Okay. You all, how are we feeling about that? You think you can, now if we met that learning objective, you can go and identify the 0 force members in a truss using this search and destroy? Feeling okay? Let's give that a try on this upcoming homework. Okay, let's talk now about a different method that we can use to solve trusses. Our methods for trusses, there's two methods. There's method of joints and there's method of sections. What those names are referring to is the types of free body diagrams that we use to solve those problems. So for our method of sections, what we need to be able to do is identify, and basically what we're doing in method of sections is we're cutting through the truss and separating and doing an FBD of either part of the truss. And so we needed to identify the location of a cut to section the truss. We also can combine method of joints to solve for unknown forces. So we can use both of them at the same time. Remember, no FBD will contradict another FBD. And then use our correct signs on subsequent calcs after finding a member force to be negative or positive. And actually, we talked about that last time. Okay, so, actually, we're not going to do that one here first. Let's go ahead. We've done this yardstick truss now a bunch of times. I hope you're getting a little bit tired of this. We're almost done with it, but we're going to use it one more time so we can tie it back into what we've already seen. And so we have like this physical representation of the example that we are doing. So method of sections, basically everything that I just said about method of sections is that we are doing an FBD to either side of any cut through a truss. So everything else is still the same. We're still going to draw all of our unknowns in tension. We still have all two force members. We still have all triangular shaped outlines. So let's look at the same example we've been working on here. So we're going to draw our yardstick truss one more time. Well, maybe a few more times. Well, we're going to need some FBDs from the yardstick truss. So here's our yardstick truss here. We're going to use the same loading case. Everything is exactly the same. We've got our AY is equal to 3.93 newtons. We have a CY that's equal to 2.94 newtons. Our AX is equal to 0. 4.905 newtons here. And 1.96 newtons over here. We have our geometry. We can throw a little bit of geometry on there. All of our distances, remember, are 27 centimeters. I'm going to label this 4 at 27 centimeters. And then our height over here, also 27 centimeters. And then let's label all of our points here. So we have A, B, C, D, E, F, G, and H. Oh, I see a question here about the learning objectives. Are the learning objectives flips? They're flipped on Canvas. Oh, I guess I'll have to check into that, Lilia. Thanks for letting me know. I will take a look at that. Maybe they did get flipped somehow. Okay, and so for this problem, we would like to find part A, CB, CG, and GH. And then for part B, they want us to find AB, AG, and FG. Let's take a look at, I'm going to mark what they're asking us to find. CB, that's this one right here. And I would encourage you to mark that as well on your notes. They want us to find CG, which is this one, and they want us to find GH. Now, if we did this with method of joints, and actually they asked us to find those with method of joints last time too, we had to start with an FBD at D, and then we went to an FBD at H, and then we could have gone to it, if to finish, we could have gone to an FBD at C. So we would have needed 3 different FBDs. There's 2 main advantages to method of sections. We can cut right into the middle of the truss. So where they're asking us to find this stuff, we can say, let's make a cut right there. And then we can go to either side of any cut through the truss. It doesn't matter what side we go to. I'm going to go to this side. It looks like there's a little bit less going on over there. Maybe not really. It's just closer to the right-hand side of there, but really not a whole lot. So the one advantage is we can go to the middle of the truss when we're doing method of sections, while with joints, we'd have to go multiple FBDs to get there. The other big advantage is that all of our forces are no longer concurrent. They all don't intersect at a point. So that means we can use the moment equation and we can solve for 3 unknowns. So we're going to do an FBD to the right. And this is, I get this, we're under the solution now. An FBD to the right of that cut through BC, CG, and GH. So if we don't cut through it, it does not get exposed. It stays internal. So we have some pieces of this yardstick that we actually did not even cut through. Like C, D, and H over here, we did not even cut through. Now we did cut through this yardstick right here. And I'm going to draw it, make it look like it's got a little cut in it. So there's we sawed through that section of the yardstick right there. And so now we're going to, again, we're still going to draw everything in tension. So we're going to have a BC. We're going to have this force right here. And we know the line of action is going to go along the length of those yardsticks because they're all 2 force members. We're also going to have a force down here that's going to be GH. And we have a CG right here. And then we have some loads. Our 1.96 newtons is applied right there. We also have a CY equal to 2.94 newtons. Get some geometry on here. Notice that I'm including a point, these points right off of my FBD. I do that just so I can see where things intersect. Like I can see that CG and GH both intersect at point G right there. And it just gives me some reference for even just naming the forces, for labeling the forces. It just kind of, it's going to help me out here. So to show that dot of that next joint over, even though it's outside of my FBD, right? Because our purple line over here cuts through all those. And so that's technically outside of our FBD, but I'm going to show it off of there. We have 27 centimeters. And then we can also show, how about we show a 45-degree angle is this one up here. Doesn't really matter where we show it. We'll show it's right there. So even though we have 3 unknowns, it's okay because we have 3 equations now. And so that's one of the big advantages of method of sections. The other one is we were able to cut right into the middle of the truss. And when we use our equations, let's just think about those equations as options. For example, if we sum forces in the x, how many unknowns are we going to have if we sum forces in the x? Leah, Walker, what do you think? How many unknowns do we have if we sum forces in the x?
At point D, or just total?
We're summing forces in the x of the whole FBD that we just drew.
Oh. 5?
Well, no, 3. We'd have BC, CG, and GH.
Oh, so we don't count the actual triangle?
This part over here, like, oh yeah, let's label some stuff here, right? So this is point C, this is point D, this is point H, right? I'll even label G right here and point B. No, the triangle, we never cut through those. There could be 1,000,000 pounds or 1,000,000 newtons in there. There could be 0 newtons in there. They're internal. They do not show up in our FBD. So when we do our equilibrium equations, they do not show up in those either. So we have 3. We have B, C, C, G, and GH. Now, let's go. So that I don't want to deal with 3 unknowns in one equation. How about if I did what if I did sum of forces in the Y? Well, sum of forces in the Y, I'm only going to have 1 unknown. I'm going to have a minus CG times the sine of 45 plus 2.94 minus 1.96. So we're treating, even though it's a truss, we're treating this now as just an FBD with forces at distances, and and only the ones that we've cut through are going to be the ones that show up in our equilibrium equation. When we solve this, we're going to find that CG is equal to a positive 1.39 newtons. Now that's pretty cool, right? We got right into the middle of the truss. We were able to get one equation, one FBD, one equation. Now, one thing that we did not do is the FBD of the whole thing, and we do need to do that first, right? We had already done that before, and that's why we were given AX and AY already and CY for this problem, right? So we'd already done the FBD. So you still do have to do the FBD of the whole thing, just like we did for method of joints. Okay, so we found CG. How about, we haven't looked at using a moment equation. Where could, we can take the moment about any point. What point would be a really good point to take it at where I'd only have 1 unknown? Brett Werder, what do you think? Any ideas on where we could sum the moments?
I would probably say sum them at C. I don't know.
Yeah, it's at C, right? That would be a really good spot. If I sum moments about C, and because look at what happens. CG and BC go away. My only unknown is going to be GH. So we can solve for GH with that one. Absolutely. Let's see. Some of the moments about C, we have the 1.96. That's going to be negative 1.96 times 27 centimeters. We're going to have, let's see, CY doesn't cause a moment. All this stuff here at C doesn't cause a moment. It looks like GH is the only thing, and that is going to be also negative minus GH times also 27 centimeters is equal to 0. So we're going to find that GH is equal to a minus 1.96 newtons. And that negative tells us that it's in compression because we drew everything in tension. So anytime we find a negative, it's compression. I forgot to label it over here for CG. We found a positive. So that means it's in tension because we drew all the knowns in tension. So GH minus 1.96. Now we could go into sum of forces in the x direction. We could solve for our last unknown. Let me show you another moment equation though. What if the only thing we haven't found is BC? What if I sum moments about G? G is not even on my FBD, but look at what happens. CG and GH both go through point G. So I can do that. I can sum the moment. Actually, when I draw an FBD, I can sum the moment anywhere. It doesn't even have to be just the next adjacent joint. I can, anywhere will work. I picked the spot that got rid of CG and GH because they both go through point G. And so we're going to find, let's see, we're going to have a BC. So I'm summing them about G. BC is going to be positive, and it's 27 centimeters. And then let's see, we're going to have CY is going to be in there, and that's going to be positive. So positive 2.94, also times 27 centimeters. And then we're going to have a minus 1.96 times 54 centimeters. That's everything that's causing a moment about point G. And we're going to find BC is equal to a positive 0.98 newtons. So I use two moment equations and one force equation. You don't always have to use an x, a y, and a moment. Now, this does not mean that I have like unlimited equations, right? I can't like sum the moments about a million different places and think like I can solve for a million different unknowns. No, the moment equation becomes redundant when you use more than one of them. They replace one of the force equations. Okay, so now we've seen method of joints, we've seen method of sections. We're going to continue talking about this very briefly on Wednesday. And actually, we just finished up the topics for the upcoming exam, which is a week from tomorrow. We'll talk more about the exam, a little bit more about the exam on Wednesday. You all have a great rest of your Monday. We'll see you then.